This is Dr. Sridhar, back to you with another video session. Now, previously we have discussed about the gross torque or armature torque. Now we have derived one expression also. That torque actually it will be generated across the armature. But we are going to collect the torque or mechanical power from the shaft. So it means from the armature to shaft, that mechanical power has to travel. So during this process, what happens? Some of the mechanical energy it may be wasted. Now, in order to overcome the air friction and windage losses, because now once that mechanical energy traveling from one point in the machine to the another point in the machine, so sometimes it has to overcome air friction and windage losses. So to overcome that air friction and windage losses, the DC motor will sacrifice some of the torque. The torque is nothing but the lost torque, or after subtracting the lost torque from the armature torque or the gross torque, you are going to get as a shaft torque. So shaft torque, it will be obtained by subtracting the lost torque or lost torque from the armature torque. So armature torque is nothing but this is the major parameter. So initially you will get the armature torque here, and again whenever it is reaching to shaft, this is the shaft, air friction in this path, you will get the air friction and windage losses. So to overcome this, some of the torque you are going to lose, that is nothing but the lost torque, or sometimes it can also be called as a lost torque. So this lost torque is nothing but this is majorly to overcome air friction and windage losses. So we can develop some expressions also, because from shaft to armature, what will be the changing parameter? Only T shaft will be changing parameter, and here actual output we are going to consider. There we have considered as a EB into IA is nothing but the mechanical output power. But here it is not the mechanical output power, because if you want to calculate the shaft to power, shaft torque means now across the shaft how much of mechanical power we are going to see after subtracting this air friction and windage losses. Now that will be the actual power in order to calculate the T shaft. So we have to substitute that output in terms of the horsepowers. So that is the case. Now that is required to calculate the T shaft. Here also this is the T shaft is equal to motor output divided by the 2 pi n by 60. That is a Newton meter. And this is also T shaft is equal to 9.55 into output by n. So this is nothing but the actual output across the shaft. Now already we have talked about this gross torque or armature torque TA, that is EB into IA by 2 pi n by 60 Newton meter, and this is about the shaft torque, and we know TA and we know the shaft torque. If you are subtracting shaft torque from the armature torque, we are going to get the lost torque. So what is the reasons for this lost torque? This is a very, very important point. This lost torque is nothing but this much of torque we are going to sacrifice to overcome the air friction and windage losses. These are nothing but the mechanical losses. One more important point is, here it is, these are the mechanical losses, air friction and windage losses. To overcome these mechanical losses, some of the torque you have to sacrifice, that is nothing but the lost torque or lost torque. Coming to the types of DC motors. So the types of DC motors, again it depends on in what way we are exciting the DC motor. Is it separately you are doing, or selfly you are exciting the DC motor? Based on this, the DC motors have been classified into two separate classification, two categories. That is separately excited DC motors, and next one is the self-excited DC motors. Now one more classification is there. If that excitation, now if we are not providing any excitation, and only that magnetic field is generated because of the permanent magnets. Now excitation means with the help of some external voltage, you have to induce some amount of electrical energy to the field coils. That is nothing but excitation. Now, why generally that we are going to prefer that excitation concept means within the small space, within the limited area, if you want to generate a highly strengthened magnetic field, certainly excitation is required. Because that much of strengthened magnetic field is not possible with the smaller permanent magnets. So that's why now that can be achieved even though with the help of permanent magnets, but space is nothing but it is a constant. So in that cases, generally people will move towards excitation. So excitation is nothing but that is a process of supplying electrical quantity, electrical energy or electrical voltage or electrical current to the field coils. So this can be achieved by inducing the magnetic poles. So one more category is there. Of course, this will be used in the toys and recorder kind of things, cassette tape recorders. In that cases, permanent magnet fields we are going to achieve with the help of permanent magnets. Otherwise, if you are coming to the excitation, there are two broad areas are there: separately excited DC motors and self-excited DC motors. Now, first, if you are taking it about the separately excited DC motor, now the field, now this is nothing but RF. Field is separately isolated from the armature. Now, this is nothing but the armature here. Now, field is completely isolated, and for that field, separately we are giving some separate DC voltage. So, separately we are giving electrical energy to the field. It means we are exciting this field separately by taking VDC. So, this is nothing but separately excited DC motor. So, remaining thing is nothing but actual electrical voltage is nothing but this is the V supply we are giving to the armature. Now, induced EMF across armature is nothing but the EB, and this is the armature resistance RA, because this internally we have some resistance here in the armature that is generally represented with RA, and the terminals of this DC meter is A and AA. Sometimes this is represented as A1 and this is also A2, and field coils are F1, F2, or sometimes we can also represent it as the Z1 and Z2. This is the standard nomenclature we are going to use to represent the various terminals, because as we studied that the DC machines have two major parts. One is the armature, next one is the field. So that's why field terminals representation is with the help of F1, F2 or F and FF or Z1, Z2 or Z double Z. Similarly, armature is nothing but either A1, A2 or AA. And internally, every armature will have a resistance that generally RA we are going to use to represent the internal armature resistance. And current flowing through this armature is IA, and supply voltage is capital V. And in this one, we are separately exciting this field by taking VDC. So if you are developing the voltage balance equation for this particular motor, because these formulas will be highly helpful for us to solve some of the important parameters associated with the DC motors, or if anybody asks us to calculate what will be the current for a particular voltage or what will be the flux for a particular voltage in this type of problems, now these formulas will be highly helpful for us. Here one of the important point you have to remember, that is a BCD. What is this BCD? This BCD is brush contact drop. So per one brush there will be a contact drop of 1 volt per one brush. On an average you can take, there will be 2 brushes compulsory. Now, on an average, you can take 1 to 2 volts or 1.5 is nothing but the BCD voltage drop. Now, if it is compulsorily, if it is mentioned in the problem, then you have to consider. Otherwise, in the solution, you can clearly mention that now by ignoring the BCD, so you can keep BCD is equal to 0 and you can proceed further to get the solution of that particular problem. Now, the field winding of these motors are energized from an external DC source, just now we have discussed. And what about the voltage balance equation? Supply voltage, it will be equal to the drop across this armature and back EMF. So, B is equal to EB plus IARA. Now, this voltage drop across are due to these brushes. This is the one brush, this is another brush. This is called as a brush contact drop. It is also one kind of drop. So, that's why we are keeping it as a plus. Now, if you are taking on the left side, it will be minus, just like drop of IARA. So, this is the voltage balance equation of separately excited DC motor. So one more category, this comes under self-excited. Now clearly, now if you could see the representation of this shunt motor, now see armature, this is the armature and this is nothing but the field connected back to back, means field and the armature and the supply. These three are parallelly connected, and the drop across supply voltage and the drop across armature and the drop across field will be same. And this is the line current is equals sum of the current at this particular point. If you could clearly observe, sum of the current it will be flowing into the armature and the remaining current it will be flowing into the field coils. So what about the, suppose at this particular point if you are applying the Kirchhoff current law, incoming current is equal to outgoing currents. So IL is equal to IA plus ISH, or this ISH sometimes is also represented as the IF. So ISH is nothing but this is the shunt current. This is how much of current it is flowing into the field winding. This is nothing but the supply voltage to the field internal impedance. So that is nothing but the V by RSH, or this is sometimes this internal impedance of the field is RSH or RF, or this is also represented as ZF or ZSH based on the terminals only. So ISH is equal, because this supply voltage is known to me and internal resistance of the field also known to me, then this is exactly in parallel to this. So the drop across this field winding is also equal to the supply voltage. So V is equal to ISH into RSH, or if you want to calculate the current flowing into the field winding, this is nothing but ISH is equal to V by RSH. Then just apply the Kirchhoff voltage law for this whole expression. Now it will becomes V is equal to EB plus IARA plus BCD. So that is the brush contact drop. So like this, we can develop the voltage balance equation. Here, one of the important thing we have to remember that the shunt field winding is made up of wires of small cross section and has high resistance. Now here, there will be two internal resistances. One resistance is nothing but the armature resistance. It is represented with RA, and one resistance is nothing but the field resistance. Now here, which one is larger in the magnitude? Generally, people will get that particular idea. And in the designing aspect itself, as much as possible, this RA is close to 0, or this is nothing but a very, very lower value. And this value is nothing but the relatively large it will have. This larger resistance of this field also helpful for us to drive maximum amount of current into the armature. So we can see maximum amount of mechanical output power. So that is the added benefit. And if you are coming to the designing aspects, now small cross-section wire, it will be used for the designing of the field. And as the resistance of the shunt field winding is high, the current flowing through it is very small as compared to that of series field winding or armature current IA. So this is the added benefit. So this is about the shunt motor. And coming to the DC series motor, the field winding is connected in series with the armature. So see, this is the field here, only very few turns, not as many turns as the shunt field is having. Now series in the series motor, the shunt field which was there in the shunt motor, it will be few of them are connected in series with the armature. Then here field is connected to the armature in series. Because of that, the name came here DC series. In the previous case, a DC shunt motor, because the field is connected to the armature in parallel or in the shunt form. So that's why that was a DC shunt motor. Here in series, so this is nothing but the series motor. So this is the positive terminal, negative terminal, supply voltage we are giving, and this is a line voltage. Through the series winding, how much of current it is flowing means I series and armature current. For this also, and here one of the important thing, whatever the flux we are going to develop across this field, series field, that is nothing but pi is directly proportional to I series, which is directly proportional to armature current. So flux is directly proportional to series current, which is directly proportional to the armature current. So the relationship between the induced EMF and the terminal voltage can be established that. So here IL, supply current, series current, IA current. These three currents are series currents, so it will remain same. So that is one important point here. We can say that current relations are nothing but the line current is equal to series currents, and which is equal to the IA current. Now these three currents are same. So this is nothing but the current balance equation. Coming to the voltage balance equation, supply voltage. Now some of the voltage will be dropped across the series winding. Some of the voltage it will be dropped across that armature resistance, and the remaining voltage appears like a back EMF. So which is nothing but V is equal to EB plus I series R series plus IARA plus additionally some brush contact drop will be there. Now if it is clearly mentioned in the data, you can take it, otherwise you can ignore this BCD. And with the help of this current balance equation, you can approximate that series current and IA current will be same. So V is equal to EB plus IA. If you can take common from these two terms, then R series plus RA plus BCD. So BCD is nothing but brush contact drop, usually 1 volt per brush. So this is the voltage performance, voltage balance equation, and this is nothing but the current balance equation. And based on the length of the field, if the field is shunted or if the field coil is only connected in parallel to the armature, then that is nothing but the short shunt. sometimes the field windings are is connected in parallel to the not only armature, in addition to the armature and the series field, then that is nothing but the long shunt. Anyhow, these are well described and well elaborately discussed in the generator. The configuration is same, but only the direction of the voltages are different in the from the generator and the motor. That's only the difference. And it is a combination of shunt and series, but shunt winding is connected across only armature, hence short shunt motor. And the performance equation, if you could see, this is nothing but the line current. Now it is divided into two parts. One is ISH, one is IA. Here IA and I series and IL, these three are same. So that is the reason IL is equal to IA plus ISH, and where IL and I series will be same. So ISH is nothing but if you are doing some performance equation. Now this one, this particular path, now this across the armature and then field are in parallel. Those not the supply, because supply minus V minus series drop is equal to drop across armature is nothing but the drop across shunt winding. So this is the very important equation. So V minus series drop is nothing but I series into R series. So this is nothing but the drop across armature. So what is this? EB, and another drop is nothing but IARA, and one more drop also you can take. There is a BCD, and which is equal to drop across shunt winding. What is this? Shunt winding is nothing but RSH into ISH. Now if you are simplifying this performance equation, now we are going to get the shunt current is equal to ISH equal to V plus I series into R series divided by the RSH. And more elaborately, we can write the voltage equal to EB plus IARA plus I series R series plus brush contact drop. This is about the short shunt compound motor. And this is long shunt compound motor. The shunt winding is connected across the combination of the armature and series. Just now also we have discussed about this. Hence, because of this only, this is nothing but the long shunt compound motor. Here, the difference between the long shunt and short shunt, if you could observe, here this is the supply voltage and the drop across the field, and the drop across armature along with the field will be same. This is the one path, this is the second path, this is the third path. So like this, if you could able to remember, this is very easy to solve the associated problems with the long shunt and the short shunt. And clearly you observe I series current and IA current will be same. So this is nothing but I series and IA will be same. And IL is equal to, this current is equal to, some of the current is coming to the shunt and some of the current is flowing into the armature. So I series plus ISH, that is IA plus ISH. So ISH is nothing but, anyhow, this is exactly in parallel to the supply voltage. So ISH is equal to V by RSH. And finally, the voltage balance equation becomes V is equal to EB plus I series R series plus IARA plus brush contact drop. So this is about the performance equations of long shunt compound motor and short shunt compound motor, and series and shunt motor, and separately excited DC motor also. These are the various classifications. These are very important. With the help of these voltage balance equations and currents balance equation, we are going to solve few more problems in the next videos, in the coming next videos. Thank you for watching this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.